Hello students. Today we're going to be taking a look at section 5.5 and I'm going to go ahead and test out a different screen recording approach where you can see my face, and I'll walk you through previously recorded notes or completed notes with classes in past years. Along with this, whatever I decide to maybe add to section 5.5 notes, I could also do a similar recording, or as I've done in the past, the screencasting that I've been doing, but also audio recording as well, just to try to give you guys some different ways to look at some of my lessons. So today, again, we're talking about completing the square. What is completing the square? Well, completing the square allows us to solve quadratic equations primarily, of which may or may not be factorable. Let's start off with just a simple property to kind of help frame a lot of what we're going to be doing today. The square root property is a property in which you're going to use it to solve a quadratic equation that is in the form of a perfect square trinomial, and in turn it must be equal to a constant. When this is the case, you're going to be able to solve your quadratic equation um, more simply, whether or not, again, it's factorable. So again, as we know, the kind of standard form depiction of a quadratic that we've noted already is ax squared plus bx plus c. Typically, we've seen that equal to 0, but it doesn't necessarily have to be. Our goal is to, in completing the square, get the quadratic to be kind of reworked in such a way where it's a binomial squared. So it's like x plus 2 or x minus 5, that kind of thing. Quantity squared equals some constant or number. So for example, solve each equation by using the square root property, round to the nearest hundredth if necessary. So the very first example you see is x squared minus 8x plus 16 equals 25. Now, to kick this particular section of notes off with this example, the quadratic equation on the left is factorable, okay? And that's a much easier kind of way to solve these particular equations when they are factorable. X squared minus 8x plus 16 is what we call a perfect square trinomial. The first term is a perfect square. The last term is a perfect square. And when you factor it such that two numbers that multiply to 16 and add to -8, well, that simply is -4 and -4. Well, -4 times -4 is 16, and -4 plus -4 is -8. So it is, in fact, a factorable quadratic, and you can rewrite it as x minus 4 quantity squared, which is very nice because then you can rewrite the left side as you see it. The right side will stay as is, and actually that number is pretty nice as well because that also happens to be a perfect square. The next up, as you can see, is square root both sides. When you square root both sides, the left side simply turns into x minus 4. The right side, the square root of 25, we know to be 5. But remember, when you take the square root of both sides of an equation and you're solving, you must include not just the positive version of the answer, but also the negative version, if you recall from Algebra 1. So plus or minus square root of 25, so positive 5 and negative 5. Now, they've also shown here the addition of 4 to both sides on both equations, such that one answer, 5 plus 4, 9, and the other answer, -5 plus 4, -1. So the solution set, in other words, where the parabola crosses the x-axis, is simply at 9 and -1. All right, part B. 4x squared minus 20x plus 25 equals 32. Yet again, we're going to take a look at the left side of the equation and see if, in fact, this is a factorable quadratic, and in fact it is. 4x squared is a perfect square, 25 is a perfect square, and as it turns out, that again is a perfect square trinomial. In this particular case, like example A, it is a factorable perfect square trinomial. 2x minus 5, 2x minus 5. You could even split the middle term on any quadratic that you want, as we learned in the past. If it's factorable, you can do so. And because this is a factorable perfect square trinomial, 2x times 2x, nicely enough, of course, is 4x squared. I'm just checking here. 2x times -5 is -10x. inside negative 10x again, so negative 10 and negative 10 adds to negative 20. And then last, negative 5 times negative 5, positive 25. So like I said, this is a factorable quadratic, and more specifically in the next step, you can see I've written 2x minus 5 quantity squared. So that is a binomial squared. Left side of the equation, like in the prior example, you can just rewrite it. It equals 32, which isn't a perfect square, but that's okay. We're going to go ahead and take the square root of both sides of the equation again. In one hand, we'll get 2x minus 5 equals positive root 32. And on the other hand, we'll get 2x minus 5 equals negative root 32. Root 32, as you can see my scratch work off to the side, can be broken up with a factor tree such that it's 16 times 2. 16, of course, is a perfect square of 4 times 4, and that actually simplifies nicely as 4 root 2. So because root 32 is 4 root 2, you have 2x minus 5 equals positive 4 root 2, but also 2x minus 5 equals negative 4 root 2. Simply add 5 to both sides of both equations, divide by 2, and then you'll end up with, for the first, 5 plus 4 root 2 over 2, and then the other 5 minus 4 root 2 over 2. This is a perfectly good way to write your final answer. But as you can see down below, this is another acceptable final answer version, as what, if you can recall, we can rewrite such that 5 over 2 is one fraction, and 2 root 2 as the simplification of 4 root 2 over 2, 4 halves, of course, being 2. And again, there are two versions of this, or two answers of this, such that one is plus and one is minus. So please make a note of that. Again, if we were to graph this, you'd see a parabola that crosses the x-axis at those two irrational roots. All right, moving on. So I did a couple of exercises here. I'm going to walk you through these. It says solve each equation by using the square root property, round to the nearest hundredth if necessary. So for problem number 1, we've got, again, a quadratic on the left, and that equals a constant there on the right. Turns out this is a factorable perfect square trinomial. X squared is a perfect square. 81 is a perfect square, as is 49 technically. It doesn't have to be, but it is, and that actually will make our problem in the end very nice as far as a final answer. This does work out such that it factors as x minus 9 times x minus 9. Negative 9 times negative 9, of course, is 81. And while you add the 2, you'll end up with the middle term of negative 18x. Just to double check to see if the foiling, in fact, verifies what we see. That then leads to x minus 9 quantity squared equals 49. If you take the square root of both sides, the square root of something squared, like we already knew, is x minus 9 in this case. And on the right side, the square root of 49 plus or minus, don't forget, 7, because it's a perfect square, so you end up with that nice value. But we're not quite done. We're going to add 9 to both sides, so you technically will have two answers. 9 plus 7, so 16 is one root, and then 9 minus 7, so 2 as the other root. Okay, moving on to number 10. So you can see here, number 10, we've got a perfect square trinomial. Because this is a perfect square, as is this. The right side of the equation, it's not a perfect square, but that's okay. We're going to be able to do the same type of analysis, like we saw in the example B up above. Because 25 is a perfect square, it makes sense then that 5 and then x, and then 5 and x again, because what, 5x times 5x is simply 25x squared. Double check yourself on that. 4, again, is a perfect square, of which, of course, 2 times 2 will give you that result. So 5x plus 2 times 5x plus 2, you can FOIL to check if we're in fact right. First, outside, inside, last. In fact, yes, first is 25x squared. Outside, inside, add to 20x, because 10x plus 10x is 20x. And then last, 2 times 2, of course, is 4. So we'll rewrite this as a binomial squared, and that equals still 75. We'll take the square root of both sides, and we'll end up with 5x plus 2. And on the right side, a little manipulation such that we know 25 times 3 is, of course, 75. Now, 25 is a perfect square, 3 is not, so you'll be able to take the square root of 25 and get 5. Root 3 is going to stay as is, so 5x plus 2 equals plus or minus, don't forget, 5 root 3. Simply subtract 2, divide by 5. This version of the answer is perfectly acceptable. What I did also do here, I didn't show the work, but if you divide everything by 5, 5/5 just gives us 1. So root 3 there at the end. So negative 2/5 plus or minus square root 3. As decimal approximations, again, it did say round to the nearest hundredth if necessary. The first version of this, the negative 2/5 plus root 3 can simplify as 1.33, while negative 2/5 minus root 3 can simplify as negative 2.13. So just to know. Now these two examples are a nice reflection of both A and B up above. Obviously problems will vary. This is just to kind of warm you guys up to the idea that you won't necessarily always get a nice rational answer in number 1. Well, obviously in number 10 we saw irrational answers. Okay. I'm going to continue on the next page here. I will likely be able to get through the examples and maybe a problem or two following that. We'll see how it goes. Whatever I don't finish, like I said earlier, will maybe become an audio lesson or a continuation in that manner. So we're going to complete the square more officially, but we're going to take the ideas that we learned on the prior page and apply them in a little bit more kind of specific, streamlined manner. To complete the square for a quadratic expression of the form x squared plus bx, you follow these steps. So the first step is to find b over 2. I'll explain where and when to find b, and we'll divide that by 2 in the first step. The next step, once you establish what b over 2 is, you square that whole quantity. And then the third step is you add b over 2 quantity squared to the original 2-term binomial, x squared plus bx. And they're going to start you off quite nicely with example 1, asking you to find the value of c that makes x squared plus 22x plus c a perfect square trinomial. So we don't know what c is, but if we follow these 3 steps up above, quite literally completing the square, it's called completing the square because we're literally completing it as a perfect square trinomial. We're going to see that then unfold the way we should, hopefully. Then write the trinomial as the square of a binomial. So step 1, identify b. Okay, if you look at ax squared plus bx plus c, not surprisingly, b is just 22 from what they gave you. B over 2, that's easy enough as well. Divide 22 by 2 and you get 11. So step 1, there you go, 11. Step 2, square b over 2, which is what we're seeing here. 11 squared, of course, that's 121. Check that step off. And then last but not least, step 3 is to take that value and literally add it to the original problem such that it's, well, because we know it to be 121, so that's what c is, we could plug it in. So x squared plus 22x plus 121. And yes, this is now officially a perfect square trinomial. And if you had to factor it, you could. It would look like what? X plus 11 times x plus 11. And if you were to FOIL it, it does in fact prove out that yes, that quadratic we just deciphered with that c value in particular is correct. The final answer, as it turns out, put x plus 11 times x plus 11 into the context of a binomial squared as they had asked, and that should suffice. Example 2, this is a solving problem. This looks like it may be our last problem technically. I'm running out of time here. So solve 2x squared minus 8x minus 24 equals 0. Now, as far as completing the square goes and actually solving it in this particular way, the very first step is to essentially get a, which in this case is 2, but to get it to equal 1. So how do I get a to be equal to 1? Well, as I've circled here on the right, it says divide each side by 2, and that's exactly what I did. So that lends itself nicely to then seeing what? X squared minus 4x minus 12 equals 0. And because a is equal to 1, we are officially allowed to go through this 3-step process again. So do exactly what you did in part A. So find b. Looks like b is negative 4 divided by 2. So negative 4 divided by 2 should be negative 2. And actually my work is down below. So negative 4, b divided by 2, negative 2. And then we'll take b divided by 2 squared. We're already actually applying step 3 there, as you can see. So what? Negative 2 quantity squared? Well, positive 4. Now, one other thing, as you can kind of see already taking shape here is, and they wrote it off to the right, add 12 to each side. Now, this is crucial. If you add 12 to both sides, you're going to have a blank spot to be filled in, one of the values of which will be 4, the value of which is a perfect square. And on the other side as well, 4. You'll simplify this as x minus 2 quantity squared. On the right side, 16. square root, add 2, 2 plus or minus 4 gives us our two final answers.